Howdy, welcome to Math 153, Elementary Statistics. I'm your instructor, Lance Curtis, and this is the lecture for sections 5.1 and 5.2. In Chapter 5, there are actually more than just the four sections that you see here, but we're not going to do the final sections in the chapter. They deal with Poisson distribution, which, I mean, if a Poisson distribution is something you need in your work, you can actually look it up then. What we're actually going to do is focus on probability distributions in general and then move on to talking about the binomial distribution, which we'll actually do in the next lecture. So first, let's actually do a little review and preview, get a sense of where we're at and where we're headed. So in chapters 2 and 3, we learned about descriptive statistics. We sampled the data, then we identified statistics that characterize the data, and we represent the data set with many different visual representations, different graphs and whatnot. And in chapter 4, we moved on and learned about probability. Now, here in chapter 5, we're going to take everything we've done and combine it together. Okay, learning about how to describe and analyze what we call probability distributions. Probability distributions are what the next section is about. So let's dive in. The key concept here is the probability distribution, which gives a probability for each value of a variable that's determined by chance. In essence, a probability distribution is just a frequency distribution, but instead of recording counts or, relative percentages, we're going to be recording probabilities for each x value along our x-axis. So that's a probability distribution, and we're also going to bring back this idea of what values are usual, what values are quote-unquote unusual, likely and unlikely. That concept's going to come back to become very useful for us. So first we need to understand random variables. If you're talking about probability distributions, this is the first thing you need to understand. So a random variable is essentially a variable that has a single numerical value. It's determined by chance, and it's basically, it represents the outcome of a procedure. Typically, we use the letter X to represent random variables. And just as we saw with data values, they can come in two flavors, discrete and continuous. Okay, discrete and continuous, they're going to mean the same thing that we've seen before. Okay, so discrete random variables are going to be those variables that we can count as whole values, whereas continuous random variables are going to be those random variables that we can count parts as well as wholes. Okay, discrete and continuous, same as what we've seen before. Now, as I mentioned previously, a probability distribution is nothing more than a frequency distribution where we're reporting probabilities instead of counts. Okay, here in the graphic you can see a number of different very common probability distributions. They all have their individual uses. Okay, what you're trying to do is model something that's happening in the real world. And so the way the outcomes of a procedure result from that procedure are going to be different depending upon what the procedure is. So you've got all these different probability distributions to describe an array of possible outcomes from whatever procedure it is you're looking at. Okay, now, regardless of which probability distribution you're using, okay, in order to be a probability distribution, your distribution must meet three requirements. The first one is there's a numerical random value x, and its values are associated with corresponding probabilities. Okay, so for every value of x within the range that's given there, there's a probability associated with it. Okay. The second requirement is that the sum of all the probabilities must be 1. Okay, this is very similar to what we've seen before when we were talking about percentiles. Okay, we're saying, look, if you're in the 89th percentile, that means the area under the curve to the left of that x value is 89% of the whole area under the whole distribution curve. Okay, that's because the sum of all the probabilities, you add them all up, they have to be equal to 1, because 1 is 100%. You can't have more than 100%. So that's like saying the area underneath the curve is 100%. That's your 1. Okay. It then follows that the third requirement would need to be that each probability value has to be between 0 and 1 inclusive. So you're not going to have negative probabilities. You're not going to have probabilities that are greater than 1. All your probabilities are going to be somewhere between 0 and 1. And this makes sense when you consider probabilities as being the area underneath your curve. You can't have less than 0 area, and you can't have more area than all the area under the curve. So the probability values must be between 0 and 1 inclusive. These three requirements together create what's called a probability distribution. Okay, now, just as we've seen before with other frequency distributions, we can calculate measures of center and variation. Okay, the formulas for calculating these statistics you can see here on the screen. Notice that we're using population parameters and not sample statistics to calculate our measures of center and variation. This is very common in probability distributions because sometimes you do actually have population that you're being represented with your probability distribution. So we're going to use population parameters to calculate the measures of center and variation. It's very similar to what we've seen before. What we haven't seen before is this notion of expected value. Okay, this is another example of mathematicians getting together and saying, "Oh, well, we got to take this concept and we got to give it a new name." And really, what I think it stems more from is there were mathematicians working in one area that weren't talking with mathematicians working in another area, and so mathematicians working in one area called it one thing. Mathematicians working in another area called it another thing, and it's really the same thing. So it's two names for the same thing. In essence, the expected value is the mean value of your probability distribution. Okay? The name of expected value is actually more common in the fields of regression analysis and decision theory. They don't want to talk about the mean value. They want to talk about the expected value. And if you've got, say, a list of x values and they each have a probability associated with it, then what value would you expect to get if you just picked one of them randomly? Well, the one we would most expect to get is the one with the highest probability, which is typically the mean or some value around the mean value. Hence, to calculate the expected value, we just calculate the mean. We use the capital letter E to represent it. And so it just need to understand that when you hear expected value, all you're doing is calculating a mean value. That's all it is. Okay? We've seen this before, this concept of expected value, even though we didn't name it, when we talked about the law of large numbers. So remember when we were doing these coin tosses? We said the more coin tosses that we do, the more the outcome tends to be what we would expect it to be. That standard that we were comparing against is the expected value, the mean value under the entire probability distribution. Here's an example to help us understand better expected value. So suppose we have this table here, probability distribution. It's describing the number of girls in 2 births. So you're looking at 0, 1, and 2, and find the expected value, variance, standard deviation of the distribution. So there are different probabilities associated with each of these different x values. Notice that we can add up all the probabilities together and we get 1 comes out. This is an important characteristic of a probability distribution. Okay, so we've got the entire area under our probability distribution curve represented here in this table. So first we're asked to find the expected value. Remember, that's just the mean. We calculate it with this equation here. And to do that, I'm going to take the x and the probability of x. So I have those columns here. I'm going to make a third column where I just multiply those two values together. So here, x times p of x, I'm just going to take 0 times 0.25, gives me 0, so on and so forth. Add everything up. That's what the sigma represents. It's a summation. Add everything up, and I get 1. Okay? This 1 is the mean value, or the expected value. That actually makes sense when you look at our probability distribution. Which of these probabilities is the highest? What's the 0.5 is the highest? Okay? So the x value associated with that is 1. So we would expect that the mean value of this probability distribution would either be 1 or somewhere close to it. And that's what we have. So our expected value is 1. Next, let's calculate the variance. We do that with this monstrosity of an equation here. So to calculate this, I'm going to need another column in my table, which I can create easily here. Label it accordingly. I'm going to calculate for each row. So the first row, x is 0. So I take 0, subtract out the mean. The mean is the expected value. So 0 minus 1 is negative 1. And I'm going to square that. Negative 1 squared is 1. Multiply by p of x. 1 times 0.25 is going to be 0.25. I repeat this calculation for the other rows, add everything up because that's what sigma says us to do, and we get 0.5. So then 0.5 is going to be my variance. Now, finally, we're asked to calculate standard deviation. I can do that with this even more monstrosity of an equation here, or I can just work smart and remember the standard deviation is nothing more than the square root of the variance. So I just take the variance and take the square root. Square root of 0.5 is 0.707. This is my standard deviation. So this is the way we calculate it. Keep in mind, what I just ran through here is the old school way of calculating the expected value. I did this so that you can have at least some understanding of where all of these measures of center and variance are coming from. In actuality, what you're going to be doing is using the technology. And oftentimes, for a particular probability distribution, you're going to be given usually the mean and the standard deviation, because those two characteristics are very important for describing your probability distribution. And then if you need the variance, you'll just take the standard deviation and square it. So you're going to be having technology to do a lot of this for you. Do you remember the range rule? Well, the range rule is going to come back to play here in probability distributions because we're wanting to know what values are unusual or usual, likely or unlikely. So the range rule is going to come back and play a part with probability distributions. So for the example we just considered, what would be the minimum and maximum usual values of that probability distribution? Well, we're going to calculate the same way we did before. We're going to take 2 standard deviations away from the mean to get the minimum value, and then we're going to take 2 standard deviations above the mean in order to get the maximum usual value. So we would expect values between negative 0.4 and 2.4 to be appropriate for our probability distribution. These are our usual values. Okay, so the question is, would a value of 3 be unusual? Why or why not? Well, yes, 3 is actually greater than 2.4, so yes, we would consider it unusual. But let's think back about the context of this problem. What we're looking at is the probability of having 2 girls from 2 births. Okay, so it's like you've got 2 births, and each one could be a boy or a girl. Okay, so there's a probability that you don't get any girls. There's the probability that one of them is a girl, and then there's the probability that both of them are girls. So having 3 girls come out of 2 births would be very unusual. Okay, what it actually means is that one of the births results in twins. That's the only way you get 3 girls from 2 births, right? And whether it's the first or the second, that doesn't really matter. So we're looking at this and thinking, wow, 3 girls from 2 births? Yeah, we would think that would be unusual because it's contradicting the actual assumption we have in the problem itself, which is that each birth is only going to result in 1 child. Anyway, there's the range rule. Okay, that actually brings us up to what's called the rare event rule. Okay, so if we use the rare event rule, what it is it's going to say is that if under a given assumption the probability of a particular observed event is extremely small, we're going to conclude that the assumption is probably not correct. Okay, so for example, we have here in the statement of the rare event rule, we have the assumption that we're flipping a coin, the coin is fair. So if we get 992 heads out of 1,000 tosses, the actual probability of that occurring is really small. And so when we get that, because that probability is so small, and that's what we actually got, then we're going to assume there's something not right. We have to look back at our assumption and say there's something not right with our assumption. Okay? The example that we just looked at, 3 girls from 2 births, is a good example of rare event rule. Okay? We actually, it should be impossible to get 3 girls from 2 births. Okay? Because, again, we are assuming we're getting 1 child from each birth. Okay? But if we actually do get 3 girls from 2 births, then that invites us to look back on our assumption that we're only getting 1 child from each birth and say, well, you know what? That assumption's probably not correct because it doesn't follow with the results we're actually getting. Okay? Another example would be what you saw in the statement of the rare event rule. If we have 1,000 coin tosses and 992 of them are heads, well, this is going to cause us to think, do we really have a fair coin? Okay? Because how probable is that result? It's not very probable if we have a fair coin. So working under that assumption, we're going to say that's not a very high probable event. It's a very low probable event. So because we assume the coin was fair and the result that we got was so improbable, then we have to include our assumption's probably not correct. We're probably not dealing with the toss of a fair coin that has an equal chance of turning up heads or tails either way. This is the rare event rule. So what we've seen so far is different ways for identifying events that are quote-unquote unusual. Again, you can't see my hands, but imagine I'm making air quotes with my fingers. Unusual. Okay? There's the range rule, where we just take 2 standard deviations away from the mean. And then we have the rare event rule, which we just talked about. Whereas if the probability of something that we get is extremely low, then it invites us to question our assumptions. Well, there's another approach we can use, and that is selecting a threshold probability value. A very common threshold that's picked is 5%. So unusually high values are going to be those where the probability of X or more successes is less than 5%. Likewise, unusually low values will be the probability that X or less successes are less than 5%. So you're just using that probability of less than 5% and saying, yeah, we're using that as a threshold, and for less than 5%, then the value is unusual. The example that you see here in the graphic on the right, the Reaper versus you. So, ladies and gentlemen, welcome to the main event. In this corner, dressed in black garb with the Sith, the undeniable, undefeated champion, the Grim Reaper. And in this corner, you. So, let's get ready to rumble! We look here at the probabilities, right, of all these different ways that people could die. And look at the probabilities. They're actually not that high. Okay, the highest one in the list is cancer here at the top. 1 in 500. Okay, 1 in 500 is 0.2%. That's really small, okay? Definitely qualifies under this threshold probability technique for identifying usual values, okay? That's less than 5%. So the probability is so small, we have to ask ourselves, the chances of dying from cancer are really low, okay? For just some randomly picked person out of the population. Now, that doesn't seem to jive when you think, wow, I may actually know a lot of people who have cancer. This isn't the probability of getting cancer. This is the probability of dying from cancer. And people today dying from cancer is a lot more rare than it used to be, okay? Because we've made advancements with technology, medical procedures that are actually used to treat cancer. There are a lot more people surviving cancer and dying from something else than there were in past generations. So the probability of you dying from cancer is really small, okay? So that means someone who died from cancer, that would be an unusual event. That's statistically unusual event, okay? Same with all of the other lists of death here in the list, because their probabilities are much smaller than what you get in cancer. The further down the list, the smaller the probability that you'll actually die from it. And look at some of the things in the list, like you got shark attack, okay? Ever since the film from the 70s entitled Jaws was released, there's been this huge public fear of shark attack. And yet, look at, 1 in 3.7 million? That's, abysmally small. dying in a plane crash. How many people in the world actually are fearful of flying in an airplane? There's quite a few. There's quite a few people who are afraid, and yet the probability that you're actually going to die in a plane crash is so abysmally small, it's not even worth considering. And yet there's all these people that are just so fearful of getting on an airplane and flying. And a lot of that has to do with the subjective probability that they see from all the media reports showing us videos of airplanes that are just, totally being devastated, exploding, coming apart, all these people dying. It's a subjective probability that we're basing against. When you do the actual math and come up with the actual probability, you see 1 in 11 million, that's abysmally small. I wouldn't even need to worry about that. A lot of that has to do with the fact that, we engineers, the engineering community, when we see a failure happen, we learn from our failures and we use that information to design better. And so we succeed more often. That pushes that rate of failure down. So dying in a plane crash, abysmally small. You really don't even need to worry about it. The main point here that we want to communicate is that there's another way to identify unusual values, and that is if you've got a probability of occurrence of less than 5%, then that value is an unusual value from a statistical standpoint. So that's all we have for this particular lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.